According to the CDC, 1 in 33 babies are born with some kind of genetic disorder. Imagine a world where genetic disease is completely eradicated or reduced by an astronomical amount. Or imagine crops, void of pests, and able to survive any condition. This is becoming possible with CRISPR gene editing biotechnology. As we gain the power to alter DNA sequences, serious ethical questions arise. Are we ready to embrace the ability to change countless lives for the better? Or will we exploit this technology in an attempt to resemble God and perform on his level? CRISPR gene editing is revolutionizing biotechnology by allowing precise DNA modifications. It's opening up huge opportunities in medicine and agriculture, but also comes with big ethical concerns that must be discussed. For this speech, I wanted to provide a foundational basis for the understanding of CRISPR and how it works on a molecular level. Following this, I want to explain its previous accomplishments as well as future possibilities if the technology isn't taken advantage of. Speaking of being taken advantage of, I would like to lastly discuss the ethical concerns regarding this technology. First, let's examine the complex molecular mechanisms underlying CRISPR. To fully appreciate this technology's historical accomplishments, as well as its enormous future potential, it is essential to comprehend these fundamental steps. Editing sections of DNA involves three main stages: adaptation, expression, and interference. CRISPR was developed from the discovery of unique DNA sequences in bacteria by Francisco Mojica in the 1990s. According to Shravan Suresh, in an article regarding a beginner's guide to CRISPR-Cas9 genome editing, the CRISPR array is encoded by a set of CRISPR-associated genes known as Cas genes. There are two major classes of CRISPR-Cas systems with 6 types and various subtypes. For this example, we will use viruses. In the adaptation stage of CRISPR, Cas proteins look for specific parts of a virus's DNA, called protospacers. They cut these sections out and add them to their DNA. A short sequence called a PAM sequence helps the Cas proteins know where to cut. After absorbing the viral DNA, Cas proteins produce precursor CRISPR RNAs, or cRNAs. These are then shortened to make mature cRNAs, which help the immune system recognize and destroy the virus. In the final stage, called interference, the mature cRNAs and Cas proteins find matching parts of the virus's DNA and cut it, helping to destroy the virus, stopping the spread of infection. After examining CRISPR's molecular mechanism of action in a virus, let's change our attention and concentrate on how this innovative technology is being used in industries like agriculture and medicine. CRISPR has accomplished extraordinary things in the past and also possesses extraordinary possibilities in the future. CRISPR-Cas-based diagnostic testing for the SARS-CoV-2 virus during the COVID-19 pandemic is a recent example of its versatility. According to Joel Eisenberg, in an article regarding the ethics of CRISPR genome editing found on the George Fox database, a major therapeutic goal for genome editing in the treatment of genetic diseases is to edit the genome of stem cells for the affected tissue of a patient. As an example, consider patients with sickle cell anemia. A single mutation within chromosome 11 causes the deformation of red blood cells, which can clog capillaries, resulting in immense pain, long-term organ damage, and even premature death. CRISPR also has agricultural applications, including genetically modifying crops to endure biotic and abiotic stresses, enhance their nutritional capabilities, and combat plant pathogens. According to the International Journal of Molecular Sciences, in an article regarding the application of CRISPR in crop quality improvement found in the George Fox database, crop quality is really important for how much crops are worth on the market. It's judged by both how the crops look on the outside and what's inside them. External traits include things like size, color, texture, and smell. Internal traits involve nutrients like protein and starch, and bioactive compounds like carotenoids and flavonoids. CRISPR-Cas9 technology has been used to improve these qualities, focusing on how the crops look, their texture, and their nutritional value. Aside from these uses, CRISPR holds great promise for improving human health and the environment, provided it is used responsibly within the controlled parameters of scientific research. This brings up the important topic of CRISPR technology ethics. We need to think about the ethical environment in which CRISPR operates as we explore its possibilities and uses. Despite CRISPR's accomplishments and possibilities, there are serious ethical concerns that must be discussed about where the line is drawn between good science and what is sinful. The biggest ethical deliberation regarding CRISPR is designer babies. With the power of CRISPR comes the ability to edit the human genome. A designer baby is genetically engineered in vitro for specially selected traits, which can vary from lower disease risk to gender selection. Designer babies represent an area within embryology that has not yet become a practical reality, but draws out ethical concerns about whether or not it will become necessary to implement limitations regarding designer babies in the future. The opponents of CRISPR, germline editing, which is editing the genome of reproductive cells, argue that this technique violates one of the most important moral principles, which is autonomy. The CRISPR supporters, on the other hand, argue that it would be immoral not to choose the best genes for you and your child, especially if germline editing could alleviate human suffering. And when it comes to the Catholic Church, Pope Francis has not specifically approved or disapproved of gene editing in general. Instead, he has stressed the importance of using scientific discoveries ethically and responsibly, especially when it comes to human embryos and the value of human life. CRISPR gene editing is transforming biotechnology by enabling precise DNA modifications, offering vast potential in medicine and agriculture. However, it also raises significant ethical issues that do need thorough discussion. In conclusion, we have looked at the complex mechanism and operation of CRISPR, as well as its many uses and ethical issues related to its application. We can grasp the scientific responsibilities and moral obligations associated with this innovative technology by comprehending these facets. The possibilities of CRISPR are there, and they are real. CRISPR has the power to prevent debilitating diseases for a child so that they might experience the world not sitting on the sidelines because of physical inability, but rather experiencing the world on the field and not just exist, but truly live. This is the potential CRISPR has, and it is the hope that I have for future children. Thank you.